presentation will cover the crew and passenger oxygen system. 2 oxygen systems, an automatic pressure breathing gaseous system for the flight crew, and a modular chemically generated system for the passengers and cabin crew have been provided. The crew oxygen system includes 2 circuits, each circuit supplied by its own oxygen bottle with cross-feed possibilities. One circuit supplies a captain and the first and second observer's oxygen masks, while the second circuit supplies the first and second officer's oxygen masks. The second officer's mask is located on the right-hand side of the flight deck below the second officer's panel. The first officer's mask is located in the right-hand console, and the captain's mask is located in the left-hand console. The observer's masks are located on the left-hand side of their respective seats. When the masks are not in use, they are stored in their corresponding compartments. A test, reset, slide control is used to test the mask in the stowed position. On the front of the oxygen mask compartment is an indicator that shows oxygen flow. No flow when black, and supplying oxygen when a cross is showing. To extract the mask, squeeze the red flanges causing the mask to inflate, thus unlocking the compartment door. The mask can then be pulled out. The picture on the left screen shows the flanges being squeezed and the harness inflated. On the right screen, the flanges have been released and the harness deflated. A manually operated normal 100% control has been provided on the mask to select 2 supply modes. N for normal gives diluted oxygen on demand. The 100% position gives pure oxygen on demand. A third supply mode can be selected using a rotary control in the emergency position. This position supplies a mask with 100% pure oxygen continuously, regardless of the position of the N 100% control. Now, let's try 2 simple questions. The first question, what do the crew oxygen subsystems supply? Answer C is correct. Now for the second question. Which supply modes are provided by the N 100% manual control? The N 100% manual control will supply either diluted or pure oxygen on demand, so B is the correct answer. Now, let's take a look at the crew oxygen control panel located on the second officer's panel. There are 4 pressure indicators, a low pressure and a high pressure indicator for each oxygen system. The high pressure indicator shows the oxygen bottle pressure, and the low pressure indicator shows regulated pressure available to the respective system. A single low-pressure valve switch will connect each oxygen bottle to its respective system, provided the cross-feed rotary selector is in the normal position. This action ensures a regulated flow of oxygen to each independent system. Located on the control panel is a cross-feed rotary selector which permits the 2 oxygen systems to be supplied by a single bottle. When in the norm position, the 2 oxygen systems operate independently of each other. When in the cross-feed position, all oxygen masks will be supplied by a single oxygen bottle, left or right as selected. The low-pressure valve on the system being cross-fed is automatically closed. The 2 low-pressure valves are electrically supplied by the DC essential bus and will remain energized when accomplishing the smoke removal procedures on the flight deck. Now that we have seen the crew oxygen system, let's take a look at the passenger oxygen system. The passenger oxygen masks are in self-contained units located above the passenger seats in the lavatories, galleys, and at each crew station. The solid-state passenger oxygen system improves safety and reduces weight. This oxygen is obtained by a chemical reaction. Each unit contains a chemical generator and either 2 or 3 oronasal masks depending on the location. The generator is activated when a passenger pulls the mask down to his face. Once activated, it cannot be stopped and will last for approximately 15 minutes. A portion of the units containing 3 masks have an additional generator and outlet for first aid purposes. The passenger oxygen control panel is located on the second officer's panel. A system-actuated green light, when illuminated, confirms the opening of the mask container doors. 25 seconds after the system has been activated, a blue timer not reset light will illuminate to indicate that the electrical power used to open the mask container doors have been removed. A reset push button is used by maintenance personnel to reset the mask container door electrical system. The blue timer not reset and the green system activated lights will extinguish. The normal position of the actuation switch is the guarded safety wired auto position. In this position, the oxygen mask will automatically deploy when the cabin altitude exceeds 14,000 feet. The manual override position is used to open the mask container doors if the automatic system fails, or it is desired to deploy the masks at a cabin altitude below 14,000 feet. Obviously, as some of you may know, we do not want to inadvertently move this switch. Now, for the last 2 questions. What does the illumination of the green system-actuated lights mean? B is correct. The passenger mask doors have opened. What is the electrical power source of the low-pressure valves? B is the correct answer. Let's look now at the portable oxygen equipment on the left side of the second officer's panel. This portable oxygen equipment consists of a bottle and a full-face mask. Note that the mask is supplied with 100% oxygen. To operate this unit, it is only necessary to open the valve on the top of the bottle. The pressure can be checked on a pressure gauge. Portable oxygen equipment has been provided to the cabin crew in the form of Aviox bottles. Single or double Aviox portable generators are strategically located throughout the cabin for cabin crew use. Before completing the oxygen system, take a little time and review the crew oxygen system. The crew oxygen bottles are located in a compartment at the front end of the forward baggage compartment. This completes the presentation of the A300 oxygen system. This slide tape presentation discusses the auxiliary power unit, in other words, the APU. The APU is an onboard gas turbine which can be started on the ground or in flight as long as the altitude is below 25,000 feet. It is used to provide air under pressure for engine starting, air conditioning, and wing ice protection from minus 1,000 feet up to 15,000 feet. It can also provide electrical power by driving at constant speed one AC generator from the ground up to 30,000 feet. This APU generator is identical to both the engine-driven generators. The APU compartment is located in an unpressurized area of the lower aft fuselage in the tail cone, separated from the other part of the fuselage by a firewall. It is ventilated by structural ventilation orifices and by a cooling fan. During this APU presentation, we are going to study the turbo motor, the fuel circuit, the oil circuit, the starting principle, the APU automatic shutoff, and the users. First, look at the turbo motor itself. Its controls and indicators are grouped on an APU panel at the middle of the second officer's panel. The APU is a turbo motor equipped with a dual rotor. Each rotor, or shaft, is independent of the other. The speed of each shaft is indicated in percentage and is displayed on the same indicator. An electronic control system assures APU control and regulation. It consists of two independent electronic units. One is the normal system, the other is the standby system. The control system switch allows selection of the control system to be used. When the switch is set to normal, the N1 rotor system is controlled by variable stator vanes according to the bleed air demand. The APU bleed valve is located at the outlet of the N1 compressor. This regulation is assured by the electronic control box. The N1 normal speed is shown within the N1 green arc of the indicator. The ground idle is 63% of N1. To maintain a constant airflow at the outlet of the APU, a flow detector measures the airflow to the pneumatic system and opens the anti-surge valve when it decreases or closes it when the airflow increases. A pressure switch detects reverse airflow. The electronic control box assures the automatic shutdown of the APU bleed valve. The N2 rotor system is also controlled at a constant speed by the fuel regulator, which receives data from the electronic control box. This constant speed is indicated within the N2 green arc of the indicator. This speed is 100% plus or minus 2%. In the standby mode, the second electronic system will control the N2 speed, but within less precise limits. 100% plus or minus 4%. N1 is no longer controlled. It is fixed at 97% and will increase as the electrical load demands increase. But the automatic shutoff, we shall see later on, remains operative. Will you please note and remember that the standby system is limited to ground use only for engine start and maintenance. The standby position is indicated by the illumination of a standby green light on. An air intake located at the lower part of the tail cone supplies the APU with air. It is equipped with a flap controlled by an electric actuator. The purpose of this flap is to provide a correct amount of air to the APU depending on the flight configuration. An exhaust gas temperature indicator gives the temperature in degrees centigrade. Now, let's look at the APU fuel system. Fuel from the left wing tank, and more particularly fuel tank 1A and the center tank, normally supplies the APU. But the right wing tanks may also be used when the crossfeed valve is open. A fuel pump switch controls an APU fuel pump which feeds the APU when the tank fuel pumps are not running. When this switch is set at auto, The fuel pump is activated only when the master switch is set to master switch position and a low pressure is detected in the supply line. That is to say, when the tank fuel pumps are not operating. When the switch is set to on, the APU fuel pump is always activated. The master switch also assures the control of the isolation valve located downstream of the APU fuel pump. The position of this valve is indicated by the isolation valve magnetic indicator on the test and monitoring panel. So this master switch in the master switch position opens the isolation valve and arms the APU fuel pump circuit. It also controls the operation of the APU electronic control box we have seen before and energizes the APU indicators and warnings. When this master switch is set to off, the isolation valve closes, the corresponding magnetic indicator turns cross-line, the fuel pump is disarmed, and the warnings and indications are de-energized. An APU fire handle assures the electrical control of a fire valve located between the firewall of the APU compartment and the isolation valve. The circuit is supplied by the DC essential bus bar. The position of the fire valve is indicated by a fire valve magnetic indicator located on the test and monitoring panel. The operation of this handle is explained in the fire protection course. A fuel pressure low light will illuminate amber any time low fuel pressure is detected downstream of the APU fuel pump. When the master switch is set from off to master switch, this warning light illuminates momentarily during the time which the isolation valve opens. The N1 compressor drives an accessory gearbox which is linked to the APU generator and to the cooling fan. A high-pressure fuel pump is also driven by the accessory gearbox. The high-pressure fuel pump supplies fuel regulator which maintains N2 at a constant value of 100% plus or minus 2% depending on the load. Now, let's say a word about the oil system. The oil quantity indicator is graduated in quarts. The minimum quantity before start must be above 5 quarts. During starting, quantity drops by approximately 3.5 quarts. At idle, N1 at 63%, the oil quantity should be above 1.5 quarts. Normal oil consumption is approximately half a quart per hour. The capacity of the tank is 10 quarts. The oil pump is driven by the accessory gearbox. A filter equipped with a clocking device is located upstream of the equipment. Furthermore, a low pressure or high temperature in the lubrication system is indicated by the amber oil light and the amber APU light on the master warning panel, accompanied by a single stroke chime. A start push button allows starting of the APU only when the master switch is in the master switch position. Regardless of the position of the fuel pump switch and the control system switch, it is possible to start the APU. The start push button, when it is pressed, illuminates blue and allows the APU to be started by an electrical starter, which is supplied through the DC essential bus bar by external power, or by the engine generators, or by the batteries. The starting sequence is automatic. During the start cycle, the push button remains illuminated blue. During the starting sequence, the amber oil light will illuminate, the same as the start push button. They stay on until N2 reaches 50%. On the master warning panel, the APU warning light will be inhibited. When N2 reaches 50%, the APU is self-sustaining and the starting sequence ends. The start push button light extinguishes, also the oil warning light if the oil pressure is correct. Except during the starting sequence, the APU is automatically shut down in the following cases: APU fire alarm on the ground, pulling the APU fire handle, oil system failures, N1 or N2 overspeed, 109% or better, EGT exceeding 585 degrees centigrade, reversed airflow through the air bleed valve, and failure of the electronic control box. The automatic APU shutdown is indicated to the flight crew by the fault light on the APU panel if N2 is greater than 95%, the APU light on the master warning panel and the single-stroke chime. The APU parameters will decrease to 0. In addition, the isolation valve magnetic indicator on the test and monitoring panel will show crossline. The APU bleed valve magnetic indicator on the air bleed panel will show crossline. And the APU generator off light on the electrical power panel will illuminate momentarily. Until N2 reaches 95%, especially during the starting phase, this EGT value is inhibited to prevent an automatic shutdown. However, the second officer always monitors the EGT value on the indicator. The same for the oil pressure signal to the electronic control box. It is inhibited when N2 is below 95%. But remember, the oil warning light remains operative and may be illuminated even if N2 is lower than 95% in the event of a low pressure or a high temperature in the oil system. Also, the overspeed and reverse airflow signals are inhibited during this phase. In addition, the maximum operating time for the starter is automatically limited to 60 seconds. Should the start push button remain illuminated more than 60 seconds because N2 is lower than 50%, the electrical supply to the starter will be automatically cut off. Again, the starting sequence is automatically aborted, not only if the starting time is more than 60 seconds, but also if there is no ignition and N2 is above 65%, or if N1 is below 10% while N2 is above 50%. It is very important to remember that any automatic shutdown must be confirmed by positioning the master switch to off in order to initiate again a starting sequence. If necessary, by setting the master switch off when the APU is running, an overspeed is simulated and the electronic control box stops the APU after a delay of 90 seconds. The APU can also be manually shut down on the ground by means of two external push buttons. One is located on the nose landing gear in the interphone box, and the other one on the refueling panel. Since the master switch is in the master switch position, any external shutdown triggers the fault light, the APU light, and the single-stroke chime. In conclusion, look at this general view of a starting sequence. When is the EGT signal inhibited? Above the fault light is a flap light which will illuminate amber when the intake flap, located in the APU air inlet, is not properly positioned. The air intake flap is fully open when the landing gear is locked down. When the landing gear is no longer down and locked, the red lights illuminate on the landing gear annunciator panels. At the same time, the APU air intake flap moves to the flight position to provide a reduced intake area, preventing an air overflow. The amber flap light illuminates during the in-transit condition. It goes off when the flap is in the correct position. As seen at the beginning of this course, the APU is used to supply air for the air conditioning system instead of using engine bleed air. It is able to supply both air conditioning packs. And last, remember that it drives at constant speed a generator from ground level up to 30,000 feet.
Eastern Airlines presents the A300 fuel system. It is a fairly simple system, easy to understand, and automatic in operation. 5 fuel tanks supply both engines and the APU. The 5 fuel tanks, numbered from the left wing to the right wing, are 1A, 1, center, 2, and 2A, and are integral parts of the wing structure. The vent surge tanks located at the wingtips are used to vent the fuel tanks. Fuel management is accomplished on a control panel at the second officer station on the flight deck. The control panel reflects the flow of fuel from the tanks to the engines and APU, scanning the panel from the bottom to the top. At the lower part of the panel are 5 fuel quantity indicators numbered from left to right, 1A, 1, center, 2, and 2A. They correspond to the location of the 5 fuel tanks. The maximum fuel quantity in each tank is as follows. Tanks 1A and 2A hold 8,210 pounds each. Tanks 1 and 2 hold 31,090 pounds each, and the center tank holds 31,150 pounds. The quantities shown are maximum capacities based on a fuel density of 6.7 pounds per gallon, and the total capacity is 109,750 pounds. However, when using the pre-selector cutoff mode of aircraft fueling, which will allow partial tank refueling, the maximum capacity is 104,700 pounds. 2 submerged fuel pumps are located in each tank, and for structural reasons, the center tank is to be used first, and then the inner tanks must be emptied before using the outer tanks. This fuel management is automatically accomplished by an electronic system between the center tank and the inner tanks, and by sequence valves between the inner tanks and the outer tanks. The sequence valves are fitted to the outer tank fuel pumps. Their purpose is to decrease the outlet pressure of the 1A and 2A tank fuel pumps, allowing the inner tanks 1 and 2 to feed the engines as long as there is fuel in the inner tanks. The switches controlling the fuel pumps are grouped in pairs above the corresponding fuel tank quantity indicators. 6 electrically operated tank shutoff valves control the flow of fuel delivered by the 2 pumps of each tank. 2 selector switches control the center tank shutoff valves, and 4 rotary selectors control the 4 wing tank shutoff valves. A cross-feed valve operated by two electrical motors allows the fuel supply to the engines to be possible from any one of the 5 fuel tanks. The cross-feed valve is controlled by a 2-position rotary selector. 2 indicators at the top of the fuel control panel relate to each engine and show the total fuel consumed by each engine. 2 fire shutoff valves allow the fuel supply to the engines to be stopped. The 2 fire shutoff valves are mechanically controlled through cables by the corresponding engine fire handles located on the overhead switch panel. The fuel flow is clearly displayed on the fuel control panel. Just remember to direct your scan from bottom to top. The APU is normally supplied from the left wing fuel feed manifold to the left engine. Of course, when the cross-feed valve is open, the APU can be fed from any one of the 5 tanks. A pressure switch shuts off the APU fuel pump as soon as the normal fuel pump pressure is sufficient. This is to prevent the APU fuel pump from operating continuously. Downstream of the APU fuel pump is the APU isolation valve. A fire shutoff valve allows the flow of fuel to the APU to be stopped. Take your time now and review the fuel system. Observe the schematics carefully and let fuel flow through the control panel. Remember your flow pattern bottom to top. Now let's see how the A300 is refueled. The A300 has 2 refueling stations, one on the bottom side of each wing. Each station is equipped with 2 standard connections. A refueling manifold connecting both refueling stations allows the aircraft to be refueled from either wing. However, it is against the rules to refuel from both stations at the same time. Complete refueling takes approximately 23 minutes. For each tank, one refuel-defuel valve is connected to the refuel-defuel line and controls the flow of fuel into the respective tank. Refueling, defueling, and transfer of fuel from tank to tank is controlled from a panel underneath the right center part of the fuselage. An overflow valve is installed in the center tank to protect the tank from overpressure in the event of a malfunction. This valve connects the center tank with the number 2 tank. A handle located on the left-hand side of the refuel panel controls the overflow valve and allows the center tank refuel-defuel valve to be electrically operated. A fuel transfer valve connects the refuel-defuel manifold to the engine fuel feed manifold. This valve enables defueling using the fuel tank pumps or tank-to-tank transfers. This valve is controlled by a handle on the right-hand side of the refuel-defuel panel. The tanks can also be fueled over wing from access panels located on the wing upper surface. A fuel jettison system is installed and designed to dump fuel from the inner and center fuel tanks only. Dumping fuel from the outer tanks is not possible due to check valves. The jettison system is controlled by two switches on the fuel jettison panel at the second officer's station. Two electrically operated jettison valves have a dual electric motor, one motor serving as backup. They are referred to as primary and secondary motors. The dump rate is approximately 1,400 pounds per minute. Let's try a question now. Where are the refuel-defuel couplings located? A, under the leading edge of both wings, outboard of the engines. B, under the aircraft fuselage. C, at the wingtips. As you can see, A is correct. Here's another question. What controls the flow into the tanks during refueling? A, the couplings. B, the refuel-defuel valves. C, the shutoff valves. The right answer is B. The refuel-defuel valve controls the fuel flow into the tanks during refueling. Now for the last question. What controls the transfer valve? A, an electric motor. B, the fire handle in the cockpit. C, a handle on the refuel-defuel panel. The right answer is C. The transfer valve is controlled by a handle located on the refuel panel. Note that on the upper left corner of the panel is a warning light labeled Pump Press Low. It illuminates when the pressure output of a pump is low. The magnetic indicator of the faulty pump will simultaneously turn to amber. This occurs, for instance, when the inner tanks are empty. The warning disappears when the pump switch is set to off. Two other warning lights labeled Reserve illuminate when the quantity left in the corresponding outer tank drops to 2,200 pounds. They are accompanied by the fuel light on the master warning panel and the single-stroke chime. The amount of fuel left allows about 20 minutes of flying time. An indicator located on the center engine instrument panel displays the total weight of the aircraft through its upper window. The total fuel weight is displayed in the lower window. A knob, when pulled, will allow the zero fuel weight of the aircraft to be set in the upper window. Pushing the knob in will add the total fuel of the aircraft to the zero fuel weight previously set to indicate the maximum weight of the aircraft. This concludes the presentation of the A300 fuel system. This presentation covers the fire detection and protection system. This system is quite similar to other current jet aircraft. The three main phases of fire protection are detection, warning, and extinguishing. The detection includes smoke detection in the avionics compartment, in the cargo compartments, and in the laboratories. Detection also includes the fire detection loops near the engine and the APU. In addition, heat sensing loops are used to detect pneumatic leaks. These leaks result in heating the loops surrounding the ducts. The warning system in the cockpit quickly identifies a warning so that the flight crew may take the necessary action. The extinguishing system uses fixed Freon bottles as an agent to suffocate fires, as well as shutting off the flow of any air which might feed a fire. These fixed bottles are installed in the engine pylons, APU compartment, and cargo compartments. Portable fire extinguishing bottles are installed in the zones which are not protected by a fixed installation. That is, the crew compartment and passenger compartments. Where is smoke detection provided? After this short introduction, let us start with the smoke detection system. It is designed to detect the outbreak of a fire long before the appearance of flames. This smoke detection is accomplished by means of new type detectors which analyze the chemical properties of the air molecules. They react to the combustion gases, whether visible or not, which accompany the beginning of fire. When the gases enter the detector, they modify the balance between two ionization chambers. This modification is amplified in order to trigger the local warning, always accompanied by the smoke light on the MWS and the repetitive chime. The smoke detectors are fitted on the air extraction duct or installed within the cargo compartments. The smoke detection system consists of 4 smoke detectors installed in the avionics compartment. 2 smoke detectors are located in each cargo compartment. 1 smoke detector is located in the forward lavatory and 2 in the aft lavatory vent ducting. In the avionic compartment, a smoke detector monitors the airflow coming from the fireproof compartment called the minimum equipment bay. This detector is associated with a smoke warning light located on the overhead panel. When this detection causes a smoke warning, it can be quickly confirmed by a smoke sniffing provision. The sniffer itself consists of a flexible hose below the right side of the second officer panel. The sniffer fan switch is at the lower right side of the second officer panel. The battery smoke detector is associated with the battery smoke light on the electrical panel. A detector monitors the airflow coming from behind the captain and first officer's instrument and circuit breaker panels. This detector is associated with the flight deck smoke light. The last detector monitors the main bay airflow. It is associated with the main bay smoke light, also located on the electrical panel. Which smoke indication can be confirmed by the sniffer? We shall now continue with the cargo compartment smoke detection. The cargo compartment smoke detectors are connected to the respective red smoke warning light on the cargo smoke detect panel. An electronic detection box is used to analyze the information from these detectors. It is located in the minimum equipment bay. The box is monitored by a magnetic indicator labeled Detect Fault. It will change from green inline to amber as soon as there is a faulty electronic card. The corresponding amber light illuminates on the front of the electronic box. The electrical and cargo smoke detect panel, common to the avionics and cargo compartment, allows the smoke detectors to be tested. For each position, when the ground test indicator light is depressed, the corresponding detector sets off the smoke warnings and the blue ground test light illuminates. The smoke detectors in the forward lavatories and the two in the rear lavatories vent duct are associated with the corresponding smoke warning light located on the cargo smoke detect panel. A second electronic detection box is used to analyze the information from the lavatory's smoke detectors. This box is also located in the right-hand electronic rack. This box is monitored by a magnetic indicator located on the laboratory smoke detect panel. As soon as there is a faulty card, this magnetic indicator changes from green inline to amber. The corresponding card amber light illuminates on the front of the electronic box. The laboratory smoke detect panel allows the laboratory smoke detectors to be tested in the same manner as for the avionics and cargo smoke detectors. What does this magnetic indicator mean? Fixed devices for extinguishing fire are provided in the cargo compartments. Two bottles are installed in the forward cargo compartment and may be discharged to either cargo compartment. An aft cargo smoke warning will cause an automatic closure of the respective isolation valves. The airflow being suppressed, the fire may burn itself out. In addition, the standard Freon-type fire extinguishing bottles are also employed to fight fire in the forward and mid-cargo compartments. On each bottle, a pressure switch is connected to a magnetic indicator. This MI will turn from green inline to amber as soon as the pressure in the corresponding bottle is too low. There are two separate lines running from the bottles, one going to the nozzle in the forward cargo compartment and one going to nozzles in the mid-cargo compartment. This allows the bottles to be discharged either to the forward or middle cargo compartment. Bottle 1 is discharged first. After 60 minutes, the discharge bottle 2 time reset light illuminates. This is to remind the flight crew that bottle 2 must be discharged to have a high enough concentration of extinguishing agent in the appropriate cargo compartment. A squib test panel equipped with a rotary selector and a blue light allows the continuity of the two resistances contained in each discharge head of the bottle to be tested. What is the purpose of the discharge bottle 2 time reset? Let us now move on to the fire detection warning and extinguishing systems. The fire detection zones are in the areas of the 3 power plants, namely the 2 engines and the APU. Conventional type fire detection loops are used to detect fires in these zones. The loops themselves are laid out in a configuration that includes several sensing elements in series and connected to a detector box. Due to the circuit arrangement, an open condition will not prevent a fire signal from being sensed. However, two open conditions on the same loop will isolate a portion of the loop from being effective. This visual shows how the continuity of the entire circuit is tested. In upper example of the test, the alarm circuit receives a signal only as a result of 100% continuity. In the bottom example, the open condition interrupted the signal flow from the alarm circuit. This visual shows the loops located in different areas in the engine. Each of the loops is calibrated at a different temperature threshold. The APU compartment sensing loops are all calibrated at the same temperature. There's one detection box for each fire-protected area. Each area is protected by two loops, side by side. Both loops must detect a fire to trigger a warning. The two detection boxes for the engines are found in the minimum equipment bay. And the APU detection box is located on the top shelf of this same rack. These three boxes are identical and interchangeable. If the loop circuitry has an open circuit, does this prevent the fire alarm? This box analyzes the information from the loops and sends signals to trigger warnings. The fire warnings are displayed in the usual way in the cockpit. In case of engine fire, here are the warnings which are displayed in the cockpit. Loop A and Loop B on the second officer fire detect loops panel. Illumination of the corresponding engine fire handle. Illumination of the master warning light. Illumination of the corresponding fuel lever accompanied by the continuous bell. In case of APU fire, here are the warnings given in the cockpit. Loop A and Loop B corresponding to the APU on the second officer panel. Illumination of the APU fire handle also on the second officer panel. And illumination of the APU fire warning on the master warning panel accompanied by the continuous bell. All 6 loops can be tested simultaneously by depressing both loop test push buttons. If both loops are operative, the normal fire warnings will occur. If one loop has failed, its loop light will not illuminate, and only the amber loop's light on the master warning panel illuminates, accompanied by the single-stroke chime. By selecting the operative loop, fire detection is still possible on the single loop. In case of engine fire, fuel lever must be set to off and fire handle pulled. When the fire handle is pulled down, the fluids that could feed a fire, such as fuel and hydraulic, are shut off. The air sources are isolated. The AC generator is tripped, and the continuous bell is canceled. As each engine is fitted with 2 fire extinguisher bottles, the next action after pulling the fire handle is to move it to the left or to the right, which will discharge a fire bottle. The pressure of each bottle can be checked by a magnetic indicator. The squibs of the engine extinguishing bottles can be checked in the same manner as the cargo compartment squibs. The fire bottles are mounted in the engine pylons as shown here. Access to the fire bottles is through this door on the outboard side of each engine pylon. Where would you normally check for a thermal discharge? Upon receiving the appropriate APU fire alarms, fire extinguishing is provided by the APU fire handle. The exterior warning is given by an aural warning and a red light at the nose gear communication panel. On the ground with shock strut compressed, automatic APU shutdown and fire extinguishing is provided. In the cockpit, pulling the fire handle causes the APU to automatically shut down. In addition to this, the continuous bell is canceled, the fuel valves are closed, and the AC generator is tripped. After the fire handle is pulled, it may be rotated in order to discharge the fire extinguishing bottle. This bottle is similar to the bottles used in the cargo and engine fire protection systems. The bottle is mounted on the forward side of the firewall of the APU compartment. Here is the bottle installation. You can see the discharge line in the external ejection pipe. And here is a photo of the red blowout disc, which is used to detect a thermal discharge. With a cold airplane, where would you check for a thermal discharge of the APU fire bottle? Now that we have covered detection, warning, and extinguishing for the areas associated with smoke detection and fire detection, it is time to view the pneumatic overheat detection. Pneumatic leaks are sensed by continuous loops on the outside of pneumatic ducts. They are similar to those used to detect engine and APU fires. The loops are calibrated according to the zones they protect. This visual shows the general zones where overheat protection is provided. In the wing, along the de-icing duct, along the APU supply duct, the pylon. The total overheat detection consists of 7 sensing loops, 2 electronic control units, and 3 manifold fault lights. The manifold in the wings is monitored by 2 dual loop systems, one A loop and one B loop. All the other zones are protected by single loops. There is also one single loop in each pylon. And there is one single loop monitoring the APU supply duct from the APU to where it joins the wing manifold. There are 2 control units which process signals from these loops. Control Unit 1 processes the 2 left wing loops and the Engine 1 pylon loop. Control Unit 2 does the same for the right wing and pylon plus the APU loop. In fact, there are basically 3 categories of manifold faults. One would be a pneumatic leak detected between an engine and the cross-bleed valve within the wing. The other would be a pneumatic leak in the pylon. and the last one would be a pneumatic leak in the APU supply manifold. The design philosophy is to automatically close the valves feeding the leak. When a manifold fault light illuminates, it triggers the pneumatic light on the master warning and the single-stroke chime. Each loop can be tested for continuity in the same manner as the engine and APU fire loops. The test switches include the press-to-test manifold fault lights and a toggle switch at the bottom of the panel. Which loop or loops trigger the fault light? This concludes the presentation of fire detection and protection systems.
Let us look at the A300 ice and rain protection system now. The units in the de-icing system are wing de-icing, nacelle de-icing, windshield de-icing and demisting, air data system probes, wastewater drain and heating and rain protection. Ice detection is entirely visual. There is no ice detector probe. To assist in checking the wings and nacelles for ice buildup at night, the wing leading edges and nacelles can be illuminated. De-icing is accomplished by using electrical power or hot air. For your information, those units on the wings shown in red require hot air, and those on the fuselage shown in green, along with the air data system probes and drain mast heating, require electrical power. To ensure reliability of the signals directed to the air data systems, it is necessary to heat the pitot probes, the total air temperature probe, the angle attack probes, and the static ports. The wastewater drain masks are heated to prevent icing, and the front windshields are provided with a windshield wiper system. The ice and rain protection controls and indicators are located on the overhead switch panel. Now, let's cover these units in detail, starting with the wing de-icing system. Only the two leading edge slats outboard of the engines need to be de-iced. The hot air supply for the wing de-icing system comes from the pneumatic manifold through two valves. As a reminder, the pneumatic manifold can be supplied by the engines or the APU. As you can see here, the pneumatic manifold is fed with air from two stages of the engine through a pre-cooler cooled by engine fan air. Each side is fed through an electro-pneumatic valve, shown here as anti-ice valves, which also controls the pressure at a predetermined value. The air is then sent to the two movable slats through a telescopic duct. The de-icing valve is controlled by a three-position switch. The on position will open the valve in flight only. The off reset position closes the valve and rearms the protection controls. The ground check position will allow the system to be checked on the ground. A magnetic indicator shows the valve position, and warning lights are associated with the system operation. Let's locate the main components we have just talked about and discuss their protection systems. The anti-icing valve is located between the engine pylon and the fuselage. The wing de-icing valve will close automatically if the corresponding fire handle is pulled. An overheat or overpressure occurs in the de-icing system, or a wing overheat occurs. It is accompanied by a fault light on the control panel and the de-ice light on the master warning panel, along with the single-stroke chime. A supply low light on the control panel will illuminate along with the de-ice light on the master warning panel, and a single-stroke chime sounds when low temperature or low pressure is sensed in the wing de-ice duct. This action does not close the wing de-ice valve. On the ground with one engine running, operation of the system can be checked by setting the control switch to ground check. The switch will cause the engine high-pressure valve to close and the pack valves, if open, to close. This allows low-temperature air to be supplied to the wing de-ice system. If a predetermined temperature level is reached, the controller will automatically close the wing de-ice valve and illuminate a temperature high light on the second officer's panel. The high-temperature safety device can be tested by pressing the light cap while holding ground check and observing that the valves close, as indicated by the magnetic indicator and the temperature high light illuminating. Remember, wing and nacelle de-ice use hot air, and windshield uses electrical power. Remember that the valve closes automatically when an overpressure, overtemperature, or wing overheat occurs. Pulling the corresponding fire handle also closes the valve. We will now discuss the wing de-icing on aircraft 215 and subsequent. Engine bleed air is used to de-ice the leading edge of slats number 2 and 3. Normally, the left and right wing de-ice manifolds are isolated from each other when the pneumatic cross-bleed valve is closed. There are 2 wing de-ice valves on each wing. They are in parallel and between the pneumatic manifold and the respective wing de-ice manifold. The left-hand and the right-hand supply switches on the wing de-ice panel each have a number 1 and a number 2 position. The number 1 position arms the number 1 de-ice valve, and the number 2 position arms the number 2 valve. Both the right and left-hand supply switches are normally selected to the number 1 position. The selected valves will open when the wing de-ice valve's switch is placed to open. Placing the wing valve switch to the close reset position will close the valves. It will also reset the valve logic following an automatic closure. This is caused by pulling the engine fire handle, provided the pneumatic crossbleed valve has been opened. This will allow the valve to be reopened for wing de-icing on the failed engine side when the valve switch is repositioned to open. The test position, which is spring-loaded to close reset, will open all 4 wing de-ice valves for a maximum of 10 seconds for a ground test. The valve's disagree lights illuminate when the valves are in transit. If the valve position disagrees with the switch position for approximately 3 seconds, it will cause the de-ice light on the master warning panel to illuminate along with a single-stroke chime. The APU supply low light illuminates with the de-ice light on the master warning panel along with a single-stroke chime when the wing de-ice is supplied by APU bleed air and the pressure drops below a preset value. However, Eastern's A300 APUs are limited to 91% N1 and therefore cannot be used for wing de-icing. Now, let's talk about nacelle ice protection, which also uses hot air. The nacelle air supply is bled from the 10th stage of the engine through an electro-pneumatic shutoff valve. The 10th stage air flows inside the double skin of the nacelle leading edge, then is dumped overboard. The control panel is located on the overhead switch panel and contains an open-close switch and a valve disagree light. This light indicates a disagreement between the valve position and switch position. If the light remains illuminated for more than 4 seconds, it will illuminate the de-ice light on the master warning panel and sound a single-stroke chime. A point of information. The nacelle anti-ice must be on for taxi and takeoff if icing conditions exist. That is, an outside air temperature of less than 8 degrees centigrade or 46 degrees Fahrenheit, and visible moisture is present. In addition, if the outside air temperature is 5 degrees centigrade or less with standing water or slush, the nacelle anti-ice system must be used. Now, let's take a look at the windshield heating system. The windshield heating control panel is located on the overhead switch panel. It is divided into two parts. The lower part controls the front windshield and the upper part controls the side windows. The front control panel has a 3-position control switch which will turn off the power to the front windshield or allow 2 power levels, high or low, to be selected. An amber fault light is associated with each front windshield. The side window control panel is identical, except that only one power level may be selected. The principle of temperature control is the same for all windows. A regulator controls the temperature of the windows between 44 degrees and 46 degrees centigrade. With the switch in high position, the power cycle is faster than it would be if the window were in low position. Also, there is a voltage difference between low and high. The amber fault light warns of a heater malfunction. If the temperature of the window decreases, the fault light will illuminate. The temperature at which the light illuminates depends on switch position. The temperature is 18 degrees centigrade with a switch in the high position and 0 degrees centigrade with a switch in the low position. If the temperature decreases to minus 60 degrees centigrade, the fault light will also be accompanied by a window light on the master warning panel and a single stroke chime. On the other hand, if the temperature increases to plus 60 degrees centigrade, again the fault light will illuminate along with the window heat on the master warning panel and a single stroke chime. A regulator malfunction could cause the temperature of the window to rise to plus 60 degrees centigrade. If this occurs, the heating is automatically terminated. In the event of this failure, a transfer selector will enable both windows to be controlled by the remaining good regulator. The window heat must be selected on at all times. If it is not, the warnings will be energized. A test system allows a windshield heat system to be tested for continuity. This can be accomplished by depressing the power test light. With the respective power switch on, the blue light will illuminate when pressed to provide a functional check of the system. The test will stop automatically after 10 seconds to avoid overheating. The light will extinguish. The safety test switch enables us to check the minus 60 degrees centigrade low level and the plus 60 degrees high level safety features. With the power switch on and the safety test switch in the temp low or temp high position, the fault light and the window warning light on the master warning panel will illuminate, accompanied by a single stroke chime. Look at the control panel. Which picture is correct? A, B, or C? Answer C is the correct answer. Remember, we stated previously that if the switches were off, the warnings would illuminate. The air data system probe heating consists of 3 independent systems: a captain system, a standby system, and a first officer system. Each has a control switch and warning lights. For your information, the total air temperature probe is not heated while the aircraft is on the ground. In case of a probe heater failure, the following warnings are triggered: the corresponding light on the control panel, the probe's light on the master warning panel, and a single stroke chime. The control and monitoring panel for the air data system probe heating is on the second officer's panel. The 3 wastewater discharge drains are electrically heated. They are provided with normal heating in flight and reduced heating on the ground. Rain protection is ensured by 2 windshield wipers and 2 rain repellent systems. The captain and the first officer controls his own wiper and repellent system from his own control panel. The rain repellent system consists of a main system shown in red and a blowout system shown in blue. The main system includes a pressurized tank and 2 solenoid valves. The corrosive rain repellent fluid is projected on the windshield through a nozzle, and air from a reservoir pressurized by the air conditioning system purges the lines after use. When we depress the button, the valve opens and a timer applies a measured amount of fluid on the windshield. If more fluid is needed, the push button must be depressed again. As before, never apply rain repellent on a dry window. On the bottle located on the left sidewall of the flight deck, you will find a nitrogen pressure indicator as well as a level indicator. The bottle must be replaced if the nitrogen pressure is in the yellow range or if the refill indication float is visible. A new concept of heating is the flight crew oxygen bottle bay heating. We heat this bay to prevent mist formation in order to be able to read the 2 indicators. This heating system is protected by a circuit breaker at the second officer's station. This completes the ice and rain protection system presentation.
This presentation covers the A300 power plant. Eastern Airlines A300 aircraft are equipped with 2 General Electric CF6-50C2 engines. They are dual-shaft, high bypass ratio turbofan engines. Takeoff thrust is rated at 52,500 pounds up to ISA plus 15 degrees. 80% of the thrust at takeoff is produced by the fan, the remaining 20% by the core engine. Each engine is equipped with a fan section thrust reverser. The low-pressure rotor is comprised of 4 stages that is driven by a 4-stage low-pressure turbine. The first stage of this compressor is the fan discharging most of its flow into the fan duct. The remainder of the fan discharge air is directed to the core engine, giving a bypass ratio of 4.4. N1 is the low-pressure rotor speed indication. The N1 indicator is the primary power setting instrument. The A300 engine instruments do not include EPR indicators. The high-pressure rotor is comprised of 14 stages. This compressor is driven by a 2-stage high-pressure turbine. The high-pressure compressor rotor speed is monitored on the N2 indicator. The combustion chamber is an annular type and is fitted with 2 independent high-energy igniters and 30 fuel nozzles. An accessory gearbox is installed on the lower part of the fan shroud. It is driven by N2. The gearbox drives the following: an AC generator, a fuel pump and main engine control, 2 hydraulic pumps, lubrication and scavenge pumps, N2 tachometer generator, and the starter. The different engine systems are starting and ignition, fuel, oil, and reverse thrust. The engine start panel provides the controls for ignition, starting, and cranking. Ignition is controlled by the rotary selector. Each engine is fitted with 2 identical ignition systems labeled A and B. System A is supplied by AC bus number 2, and System B is supplied by the AC emergency bus through the corresponding engine fuel lever. If starting on battery only, circuit B can be used. Ignition is not electrically supplied during smoke drills. This schematic shows you how the ignition rotary selector works in the start or continuous relight position. When the rotary selector is positioned to crank, ignition is terminated. Engine number 1 and engine number 2 push buttons are used to engage the starter. Now for a look at the engine starting system. You should remember that a pneumatic starter drives the N2 shaft. The starter can be supplied with air from 3 different pneumatic sources: an opposite operating engine, a ground supply, or from the APU. An open blue light on the engine start panel indicates that the starter valve has opened, allowing the pneumatic source being used to supply the starter. To start the engine, the arm start abort switch is set to the arm position. This position completes the circuit to the start push button. A switch in the N2 indicator will hold the start button in as long as N2 RPM is less than 45%. To start the engine, ignition system A or B is selected. The system selected is ready to be electrically supplied. The arm start abort switch is set to arm. The start push button is electrically supplied by the DC essential bus. All the available air is used to start the engines. Setting the arm start abort switch to arm causes both pack valves to close if their switch is in the automatic position. The yellow light in the push to start button will illuminate during the pack valve transit. Both start push buttons will illuminate as long as a pack valve is not closed, and the 2 fault lights on the air bleed panel will remain on as long as a corresponding pack valve is not closed. The corresponding pressure gauge on the air bleed panel indicates available pressure for starting. When the start push button is depressed, it remains depressed. The start valve opens and air is routed to the starter. The start valve open blue light will illuminate, and the ignition is armed. When the engine N2 reaches 45%, a switch in the N2 indicator opens and causes the start push button to pop out, the start valve to close, the blue open light to extinguish, and the ignition circuit is deactivated, completing the start sequence. The arm start abort switch is positioned to start abort so that the air conditioning pack valves may reopen to allow air conditioning and eventual pressurization of the aircraft. If the APU air supply is used to start an engine, when the start push button is depressed, it causes the APU N1 to increase to 91% in order to provide sufficient air from the APU for engine starting. At the end of the starting sequence, when N2 reaches 45%, the start push button pops out and the APU RPM returns to its previous state. In the event of a restart in flight, the lighting sequence of the start push buttons is modified according to the pack valve position, as will be explained in the air conditioning course. If the start valve remains closed during start due to an electrical failure, the open light does not illuminate and engine start is not possible through this method. But the start valve can be manually opened on the ground through a door on the engine nacelle. Positioning the arm start abort switch to start abort will discontinue the start attempt, and the following actions will occur. The start push button pops out, pack valves open, start valve closes, open light goes out, ignition is deactivated, and APU, if used, returns to its previous state. Now for a look at the engine fuel system. Here is a general schematic of the fuel system that is read from the bottom to the top. Now we will see each part in detail. The engine fuel pressure is supplied by a low and high pressure pump. The fuel pressure is sensed between the 2 pumps by a pressure transmitter, and is shown on a fuel pressure indicator on the second officer's panel. These pumps are driven by the same shaft from the accessory gearbox. The fuel passes through a fuel oil heat exchanger in order to cool the oil and prevent the fuel from icing. Downstream, we find the fuel filter with a bypass valve. This bypass is designed to ensure a fuel supply in the event the filter should clog. If clogging occurs, a differential pressure transmitter activates a fuel filter clog light on the second officer's panel. Then the fuel enters the main engine control. The main engine control obtains and regulates the N2 selected by the throttle. The fuel flow is regulated in order to maintain a constant N2 for a given throttle position. The main engine control receives the following information: temperature at the low pressure compressor inlet, N2 RPM, pressure at the high pressure compressor outlet. Also, it controls the position of the variable stator vanes relative to the high pressure compressor. The main engine control also controls the ground and flight idle. In flight, idle produces approximately 5,190 pounds of thrust. Ground idle delivers about 1,740 pounds of thrust. Ground and flight idle are controlled by the nose gear proximity switch. A fuel shutoff valve is provided at the main engine control output. This valve is controlled by an electrical motor through a flexible control. The motor is electrically actuated by the engine fuel lever, which is locked at the on or off position. At on, the shutoff valve opens and allows simultaneously ignition system A or B to be used. With the fuel lever in the on position, it will illuminate red in case of an engine fire. A magnetic annunciator, labeled high pressure valve actuator, indicates an electrical failure of the actuator. An associated press-to-test push button is provided to simulate a failure at the high-pressure valve actuator and to test the magnetic annunciator. Before reaching the nozzles, the fuel passes through a flow transmitter. This flow meter gives information to an instantaneous fuel flow indicator labeled fuel flow on the center instrument panel. The total fuel used per engine is shown on the second officer's panel. A fuel used reset push button, when depressed, resets the indicator to 0. Now, a few words about the engine oil system. The oil supply tank is on the right side of the engine with an access door in the fan cowl. The tank has a gravity fill cap and a dipstick in addition to a pressure fill port and a pressure fill overflow port. An oil quantity transmitter provides information to an oil quantity gauge on the second officer's panel. This tank supplies oil to the engine oil pump. After the supply pump, the pressure is sensed and low pressure will be indicated by an engine oil pressure low red light on the master warning panel and accompanied by a single stroke chime. Oil pressure is shown by an oil pressure indicator on the second officer's panel. Notice that the oil pressure and the warning light receive their information from two different transmitters. Oil pressure is a function of N2, and the engine oil pressure low warning comes on when the oil pressure is lower than 10 to 12 psi. Oil is removed from the oil sumps by means of scavenge pumps. Oil temperature is sensed at the output of the scavenge pumps and indicated on the oil temperature indicator on the second officer's panel. The maximum oil temperature is 160 degrees centigrade. Transient temperature between 160 degrees centigrade and 175 degrees centigrade must be limited to 15 minutes. Then the oil passes through a filter that is protected by a bypass valve. The oil is then cooled by a fuel oil heat exchanger and returns to the tank. Blockage of the filter is indicated by an oil filter clog light on the second officer's panel. Reverse thrust on the A300 is accomplished by diverting fan airflow in a forward direction. To accomplish this, the outer cowls move rearward and the blocker-type doors divert the fan airflow in a forward direction to provide reverse thrust. The cowls and doors are pneumatically operated by its respective engine. The reversers can also be operated by any pneumatic source that will pressurize the pneumatic manifold, an example, APU or external air. Reverser operation is controlled by reverse levers hinged to the throttles. Each lever will be unlocked from its idle position when the main gear is compressed and the corresponding throttle lever is at the forward idle position. As soon as the reverse lever is unlocked, the outer cowls move back and the blocker doors close. The reverser unlock lights above the N1 gauges illuminate, indicating the reversers are unlocked. After a short travel upward, the reverse levers reach mechanical stops. These stops are removed when the reversers are fully deployed. This motion takes about 2 seconds. The green reverse lights illuminate and the amber unlock lights extinguish, indicating that the reversers are in position and reverse thrust may be applied. Reverse thrust is applied by moving the reverse thrust levers upward and the throttle levers remaining in the forward idle position. As soon as the reverse levers are unlocked, the ground spoilers extend if their control handle has not been armed. Part 2 will now show us the engine controls and indicators. On the center instrument panel, 4 indicators show the following engine parameters: fuel flow, N2, EGT, and N1. Each fuel flow indicator is fitted with a counter displaying digits of the same value as the pointer. In the event of an electrical failure, the pointer returns to 0, but the counter displays the last given value. The N2 indicator is fitted with a digital counter giving the same value as the pointer. In the event of an electrical failure, a red flag covers the counter and the needle returns to 0. A red mark on the dial shows the maximum allowed N2. A red pointer in front of this mark will be driven by the N2 pointer in the event of an overspeed. This red pointer remains at the highest overspeed reached. When the N2 pointer reaches the maximum N2 shown by the red mark, the red engine N2 high warning light illuminates on the master warning panel and is accompanied by a single-stroke chime. The EGT is indicated by a pointer and a counter. The exhaust gas temperature is sensed between the high pressure and low pressure turbine. In the event of an electrical failure, a red flag covers the counter and the pointer returns to 0. A red mark on the dial shows the maximum EGT allowed. A red pointer in front of this mark can be driven by the EGT needle in the event of an overheat. This red pointer remains at the highest overheat that is reached. When the EGT exceeds the red mark, an amber light comes on at the lower right-hand corner of the indicator and is accompanied by an engine EGT amber light on the master warning panel and a single-stroke chime. The N1 indicator is identical to the N2 indicator. In addition, it is provided with an N1 limit digital counter in the upper part of the dial. An N1 limit setting knob on the lower right-hand corner is marked with an amber triangle. This knob has two positions. Pushed in, the limit counter is blanked. Pulled out, the N1 limit counter is readable. When this knob is pulled out and turned, the N1 limit counter moves, and an amber N1 limit index moves around the dial. Both devices show the same values. We have seen that when this knob is pushed in, the N1 limit counter is blanked. But note that at this moment, the N1 limit index is coupled to the N1 limit computer. When this computer is electrically supplied and no mode is engaged, the index shows 0. An indicator maximum pointer reset push button on the central panel, when pressed, resets the N2, EGT, and the N1 maximum pointers to their normal value after an overheat or an overspeed. The N1 limit computer computes the maximum N1 for each phase of flight. It also indicates the total air temperature. The computed N1 is the reference value to obtain the optimum performance for a given phase of flight. The engine type, 50-C2, is displayed in the N1 limit window as soon as the computer is electrically supplied, if no mode is engaged. To compute the N1 limit, the computer uses the following information: Mach number and altitude from air data computer number 1, total air temperature, engine air bleeds, pneumatic users, and the mode selected. When one mode is engaged by depressing the corresponding push button, it illuminates green, except the flexible takeoff, which is amber, and the corresponding N1 limit appears in the window. The engagement of one mode disengages the mode previously engaged. Dashes appear in the N1 limit window in the event of an ADC1 failure. Note that total air temperature still appears. A few words about the different modes. Takeoff, or TO mode. During takeoff, the N1 limit value increases according to the speed and is frozen after 60 knots. This value must not be exceeded. Note that the N1 limit value should never exceed 120%. Flex TO, or flexible takeoff mode, may be used when maximum thrust is not required according to aircraft weight and takeoff conditions. The N1 limit depends upon a fictitious temperature that is manually set into a flexible takeoff encoder located on the lower part of the panel. This mode is also frozen at 60 knots during takeoff. The use of takeoff and flexible takeoff modes will be explained in the performance periods of this course. Go-around, or GA mode, is automatically engaged in the computer when either go lever, located on the throttles, is used, provided that the flaps are extended more than 5 degrees. MCT mode means maximum continuous. CL mode means maximum climb, and CR mode means maximum cruise. The TAT window shows the total air temperature, but may be in error when the aircraft is on the ground due to the lack of airflow over the TAT probes. When the test push button is depressed, N1 limit shows 8888, TAT shows plus minus and 88, all mode push buttons illuminate, and the N1 indicator indexes move to the maximum indication of 120%. Note that this test is inoperative when the go-around mode is engaged or when the auto throttle is engaged. The flexible takeoff selector makes it possible for a crew member to insert a fictitious temperature for a takeoff with an adapted thrust. This flexible temperature must fall within certain parameters. It must be greater than OAT. It must be greater than ISA plus 15 degrees. it must be limited to a maximum of ISA plus 35. If a flexible temperature less than or equal to the OAT is selected, then the flex readout will show all dashes. The warning lights relative to the engines are located on the upper part of the master warning panel. They are engine 1 or 2 oil pressure low, red, engine N2 high, red, and the engine EGT amber. Note that the engine oil pressure low warning light can be energized only when the high pressure fuel lever is at on and that the engine N2 high indication is common to both engines. The following indicators are located on the second officer's panel: vibration monitor, fuel pressure, oil quantity, oil temperature, oil pressure, and nacelle temperature. We will now explain the function of these indicators. The vibration indicator gives engine vibration amplitude according to the fan turbine selector position. When the test push button is depressed, both indexes should move to a value between 6 and 8 on turbine or fan position for a proper test of the indicator channel. The nacelle temperature indicator monitors the temperature between the engine and the cowling. A high temperature in this area would indicate a bleed manifold leak. Fuel pressure is sensed at the engine fuel system just prior to the high pressure pump that supplies the main engine control. Normal fuel pressure with engines running is 75 psi or greater. Oil quantity indications are sensed at the oil tank. Minimum oil quantity for dispatch is 10 quarts plus 0.5 quarts per hour of planned flight. Maximum oil quantity indication is 18 quarts. Oil temperature is sensed in the return line to the tank just prior to the strainer and the fuel oil heat exchanger. Normal maximum oil temperature is 160 degrees centigrade with a maximum transient of 175 degrees centigrade for 15 minutes. Minimum oil temperature for engine start is minus 40 degrees centigrade. Oil pressure is sensed prior to reaching the bearings and shafts. Minimum oil pressure is 10 psi at engine idle. Normal oil pressure is between 30 to 90 pounds. The throttles and the associated reverse levers move forward and rearward to achieve maximum power and idle. The throttles are connected to the MEC, main engine control, or fuel control. The MEC governs the flight and ground idle parameters. Flight idle is 75% N2 and 41% N1. Ground idle is 65% N2 and 24% N1. Flight idle changes to ground idle when the nose gear is compressed for more than 5 seconds. Air bleed at various engine stages ensures reverser operation, nacelle and wing de-icing, cabin pressurization, air conditioning and hydraulic reservoir pressurization, and air for cross-bleed engine starts. Reverser operation is accomplished by positioning blocker doors in the fan duct. The core engine has no reversers. Reversers utilize 14th stage bleed air. Caution: the reversers will operate from any air source that pressurizes the bleed manifolds. Nacelle anti-icing utilizes 10th stage bleed air. Located on the left and right-hand side of each engine cowl are various doors, ports, and access panels. However, each door or panel is inscribed for easy use.
This schematic of the A300 highlights each of the exits and jump seat positions. At the L1 door, there are two jump seats. L1A on the forward bulkhead, which faces aft. Directly across from L1A is the L1B jump seat, which faces forward. On the right side of the cabin, the R1 jump seat also faces forward. L2 and R2 are forward of their respective doors and face aft, as do L3 and R3. The jump seats at L and R4 are also forward of their respective doors and face aft. However, these are referred to as the L4A and R4A jump seats. Additional jump seats are located aft of the doors and face forward. These are referred to as L4B and R4B jump seats. For greater access, emergency equipment on the A300 is located relatively close to each of these jump seats. At L1A, there is a lighting control panel above the jump seat. The emergency light switch is located on this panel in the upper right-hand corner. This is the jump seat at L1A. While checking equipment, always test your jump seat. Ensure that the seat belt and shoulder harness are working properly. In the compartment next to the jump seat, there is a walk-around oxygen bottle. Below the jump seat is a compartment which houses crew vest and demo equipment. Opposite L1A is the L1B jump seat. Next to the seat is a walk-around oxygen bottle. Below that, a CO2 fire extinguisher. Crew vest and demo equipment are in the seat bottom compartment. You'll also find 3 of these. This small gauge tool is used to open oxygen compartments that fail to open automatically. Also on the left, in the first overhead compartment, there is a megaphone, transmitter, a first aid kit, and water bag kits. Behind the last row of seats in first class, there are 2 extinguishers, a CO2 here on the left and an H2O on the right. In a compartment above the closet on the left is a container of 10 spare life vests. On the right side of the cabin at R1, there is an oxygen bottle outboard from the seat. Below, the H2O extinguisher. And in the seat bottom compartment, demo equipment and crew vest. A quick review of the remaining jump seats reveals a very similar layout. L2 has a dual Aviox bottle with crew vest and demo equipment under the seat. R2, the same. L3 also has the dual Aviox walk-around bottle and a crew vest and demo equipment under the seat. R3 has the dual Aviox walk-around, and in addition to the crew vest and demo equipment, you'll find 3 more small gauge tools for opening oxygen compartments. At both the number 2 doors and the 3 doors, there are marked compartments, as you see here. The FA purse stowage compartment can be opened with a cockpit key and should be locked for all takeoffs and landings. R4A has the single Aviox bottle, 5 spare life vests in the side compartment, and crew vest and demo equipment under the seat. L4A is exactly the same. Above the L4 seat, in the last overhead compartment, is a megaphone and first aid kit. On the bulkhead behind the last row of seats in this section, there are 2 more extinguishers, the CO2 on the left and H2O on the right. The last 2 jump seats are the L4B and R4B. These are additional jump seats that stow away into the bulkhead. To remove them, simply pull the lever at the bottom and swing the seat out. Lower the bottom onto the locking pin and push down. To release it, push the button on the side, lifting the bottom off of the pin. Swing the seat in until it latches into place. At both seats, there is an oxygen bottle in the compartment below the seat. Forward of this is a compartment housing a crew vest and demo equipment. This completes the equipment check in the cabin. There is additional equipment in the cockpit. And while we are not responsible for a visual check here, it's good to know what is available to us. There is a first aid kit, CO2 extinguisher, and fire axe on the bulkhead next to the engineer's seat, and a gaseous O2 walk-around bottle with full face mask on the other side behind the first officer's seat. There is also an emergency light switch located on the panel above the first officer's seat. All oxygen on the A300 is chemical, with the exception of that used in the flight deck. First aid oxygen is administered from the Aviox chemical bottles located at each flight attendant jump seat. Emergency oxygen is also chemical. Each passenger service compartment houses a chemical oxygen canister which will emit 4 liters for 10 minutes. In a decompression, each compartment will open automatically. Masks must be extended fully for oxygen to flow. Compartments can also be opened manually, but only with the use of a small gauge tool. This tool may be found in 2 places on the aircraft. One is the seat bottom compartment at the L1B jump seat, and the other is in the seat bottom compartment at R3. After the decompression, any mask with the pin pulled will emit supplemental oxygen. There are 8 door exits on the A300. 2 of these, L3 and R3, are smaller emergency doors. The rest are large passenger loading doors with dual-lane slide rafts. Despite the size of these doors, they are remarkably easy to operate. First, familiarize yourself with some of the door's features. At approximately the center, there is an arming lever under a clear cover. This lever will either engage or detach the slide bar as indicated above. Whenever the door is in detach, notice this red pin flag. This means the door may be opened without deploying the slide. To open the door in normal operation, ensure the lever is in the detach and lift up on the operating handle. The door will move outward and slide forward along the fuselage. To close the door, depress this black gust lock button. Slide the door back and return the operating handle to its original position. To ensure the door is closed properly, check the 2 door locking indicators at the top. If the door is properly closed, the word locked will appear in the color green. If it is not properly locked, the word unlocked will appear and the color red. When the slide is engaged, the door is air assisted. It therefore must be released quickly after pulling up the operating handle. The prescribed method is to pull up and immediately open the palm and push away. To engage the door before takeoff and landing, the pin must first be removed and then move the lever to the engaged position. In the event of an actual emergency, ensure the door is engaged and then open it. Pull up, open palm, and push out. These doors are not to be cracked or opened by the flight attendant. Only the agent or caterer may do so. The L and R3 doors are smaller. They do not have slide rafts, only single-lane slides, and in an emergency, they are not air-assisted. These doors have much the same features as the larger doors. There is the arming lever, operating handle, this time with a cover, and a single door locking indicator at the top. To open the door, lift the handle, push the door out, and slide it along the fuselage, just as with the larger doors. To close the door, grasp the handle at the center, which releases the door, sliding it along the fuselage, pulling it in, and returning the operating handle to its original position. There is no gust lock on this door. This handle does it all. The last exits we will review are the cockpit windows. There are 2, one on either side of the windshield. To open, push down on the black knob and pull it toward you, then slide the window back until it stops. Using any one of the inertia reels, egress through the window and allow yourself to fall free. The inertia reel is designed to gradually lower you to the ground. All doors on the A300 have inflatable slide rafts, except for the L and R3 doors, which have narrower single-lane slides. This program demonstrates the use of the slide rafts in a water ditching. A300 slide rafts will inflate automatically when the door is operated in the emergency or armed position. Once the aircraft has come to a complete stop and the raft is inflated, 3 able-bodied persons begin the tasks that they were briefed for. The first person goes to the far end of the raft, assisting other passengers and evenly distributing them on either side. The second person performs the same task in the closest end of the raft. This we will refer to as the forward end. The third person is responsible for detaching the raft from the aircraft. They first lift the Velcro, then pull the white tab and undo the lacing. Once the raft drifts free, it is still attached by a lanyard. Remove the knife from the marked location on the front of the raft and cut the lanyard. If there are still passengers to board, they must do so from the water at the boarding stations at either end of the raft. Rafts may be attached or passengers pulled in by use of a heaving line close to the boarding station. There is also a sea anchor close to stabilize the raft. Survival gear must be pulled in immediately. It is in 2 separate packages attached by a lanyard floating at the forward end of the raft. One package contains the canopy, which must be erected. Inflated tubes on the sides of the raft act as a canopy supports. Metal center supports accompany the canopy, and these should be distributed and passengers instructed on how to attach them. Rubber supports must be placed on Velcro patch and then secured with the attached string through the eyelet on either side. Tubes at the forward end must be unsnapped and given time to inflate. Once the center supports and tubes are ready, spread the canopy out and instruct others how it is to be erected. The canopy is placed over the tubes and support rods and secured by attached string at each location. Once the canopy is erected, you may distribute additional survival gear as it is needed. While the need to transport a slide raft from one exit to another is unlikely, it is important that you understand the procedure. Ensure that the slide arming lever is in the armed position. Remove the hard cover of the slide pack by pushing down on the 2 release buttons. Then, pull in and down slightly to clear the package. Once free, stow the cover out of the way. To remove the pack itself, push the girt bar release lever located under the container on the hinged side of the door. Pull the red release handles on the front of the package. Two able-bodied passengers should now assist you. Instruct them to grab the white handles on either side of the pack to transport it. Lift simultaneously and remove the raft from the door. Use caution when removing the package. Try to restrict movement of the girt bar. This will prevent the slide raft from accidentally inflating. Once removed, secure the girt bar to the package with the red tab in the center. The slide raft may now be carried to the alternate exit. Carry the container with the metal side up. Place the package at the new exit with the metal side up and the girt bar toward the door. Pull the cables of the release mechanism at the top edge of the package. Before pulling the cable with the pin, however, use the pin to rotate the release bar until it releases the metal cover. After removing the cover, insert the girt bar in the brackets at the base of the door and roll the package out of the door. It should inflate automatically, but you must pull the red handle to be certain.